this talk of us is a vindication of what Graham and Jordan have discussed in the morning, and I'm very proud to say that we both are like recent immigrants, 2 to 3 years in Canada, and we are here speaking in front of you guys. So it's a vindication of what Jordan as well said in the morning. To start with, re-architecting legacy machine learning systems. Why is it important, right? We are a product-based company, and we take research to production. And my personal opinion is anything in production becomes legacy soon. So when it becomes legacy, your models they deteriorate in production, so it impacts the end revenue. So this is a very practical talk talking about how you build, re-architect your systems over and over again. So this is the brief agenda of the talk. So before we go into the talk, I'll just quickly touch upon what TradeRev is, what its business model, and where do we use machine learning into. So TradeRev is a product-based company. It's an online auction house for used cars. It's a B2B space business, dealer to dealer. And think of it as auction house. The dealers will list their cars online, and the other dealers can bid on it. So this was founded in like 2009-ish time frame, and a couple of years back, this was acquired by a US-based MNC, Car Global, which has lots of brands under its umbrella. So we are part of Car Global. Car Global's primarily business is into physical auctions, and we are trying to pitch in with online auctions and get the latest tech into the auto industry. These are just some of the numbers on Car. All right. So before we go deeper into the talk, these are the three main verticals where we use machine learning within TradeRev, and we use the public name for that platform is H. It's basically three verticals here. I'm forgetting the name on the famous person on which we put the name on. I'll recollect and come back to you. But the three main verticals are regression, we have computer vision, and we have recommendation systems. So the use case for regression is, think about a bid coming up on a car. We want to predict what's a good starting point of the price. We don't want a low bidding on the price, like a $10,000 car. We don't want someone to bid at $50. So based on the price, on the condition of a car, we suggest a good, bidding price. Now there's a listing price. Whenever the dealer uploads or lists his car, what could be a good price at which he can, sell it. Computer vision, like since you're buying cars online, right? So you have to figure out, first of all, whether it's really a car or someone is selling a bus or a truck or maybe a horse cart on your platform. So that's where we have a car, no car. The other thing is we have a cool system in which we take a video of the car, and from that we can figure out the passenger side, the back side, the front, the console of the car. And there's a cool video on the TradeRev channel. You can watch out and you can appreciate how cool that feature is. A recommendation is a typical use case where we are recommending cars to the dealers. So today's topic is primarily dealing on the regression framework. So when the initial product on regression, basically the price prediction, came up, this was 2-3 years back, and it was getting a system quickly into production. Early stages of the product, early stages of research. So this was the initial architecture where we have the typical pre-processing pipeline, the training, validation, testing, and the inference. So think about this as a lambda function which is triggered at a regular basis. So this is part of the training job. It reads the historical data on which we train, and then we run a parallel training jobs using AWS batch, and then the models are and the associated metadata is stored into a S3 bucket and RDS clusters. Now during inference phase, we again have a lambda function which is basically accepting a HTTP request. It's a REST API, and this has the features of the car. So what we're trying to do is, based on the condition report or features of a car, make, model, age, mileage. These are very obvious features. Whenever you go to buy a car, you'll have some things in mind, and you hit the API, and during each invocation of the API, you will download the models in real time and then do a predict on that. This was good for the initial phase. Now what happens is, as the business grows, there are more use cases, there are more requests coming in. So at a point of time, this solution does not scale. It cannot add, it's difficult to add new features. There are no unit tests, there are no automation frameworks, there are no, the code is a monolithic beast. It has, I'm just showing one part of the entire code, but it has other pieces like ETL code, recommender systems, everything in this place. So it becomes difficult to scale your product, to add more features onto it, more use cases onto it, and as and when business grows, the product needs more and more features, and which is a good problem to have. So your business is growing, so you're always happy. So we had more use cases, and we were not able to break the monolith really well. We spent a couple of months on redoing things, re-architecting, refactoring, and all that stuff, but somehow it was not a worth investment of time. So to get the feature in time, we came up with the intermittent system, in which this part of the system is the legacy which I showed on the previous slide, and we built new systems, the new machine learning systems, which can solve our use cases. So the use case 1 is the bidding price, which I told you. The use case 2, 3 are other proprietary use cases, which I'm not able to share. And the whole process was, I can explain that in the AWS diagram as well. So this was our intermittent ML system from AWS perspective. Here the AWS Lambda for the first one is the legacy API for us, and then this one is the API for the second machine learning service with a different model altogether, and then you have a third service, a different model again, and then at this point, this is the new API. So the client is behind, is hitting this API, and then we have a sort of a mini microservice model where you hit all the 3 APIs over the REST interface, and then you add some business logic in the front end Lambda, and based on your use case, you start picking this service, this, or a combination of others. Now the challenges, as you can really see, there's a lot of duplicate code. Pre-processing might be common in all the 3 services. The infrastructure resources are the major concern, because we have 3 independent infrastructure in the sense AWS resources. We have 3 independent pipelines, we have 3 independent inferences, and with that it becomes difficult to manage it, maintain it. As I earlier said, the independent microservices, right? So all the 3 services having independent stuff everywhere. And then more than that, the challenge is, if you want to add new machine learning models, what are you going to do? Are you going to create another 4th microservice, 5th, 6th, 7th? It's not going to scale for you. So after this, we have more feature requests coming in. So went back to the drawing boards, thought a lot about it, and then we come to the current machine learning system. So this is our current machine learning system at a very high level. So where what we have done is we have encapsulated all these services as modules. So if you see this pre-processing module, it is going to do the pre-processing data transformations, all your outlier detection, cleaning, and then we have the training module. The training module is the beauty about the training module is now we are not going to add independent microservices. We are going to add modules within this module itself. So you have think about it as you have a modularized machine learning system where you can plug and play your pre-processing models, you can plug and play your training models, let's say it's XGBoost or it's AdaBoost or random forest, whatever. So you can just start plugging in. And then you have the inference module. And based on this, you get a price. But everywhere you are building the system, you're putting a lot of checks and balances in terms of automated tests, in terms of automated deployments. And then on top of this, we have these use cases which can solve various problems for us. So with this architecture, we can add more features, we can add more use cases, and ship the product out quickly. And the other thing is, all this is contained in Docker containers. So as we move further down the line to, let's say, Kubernetes or the other clusters, we can have these our code as part of the Kubernetes cluster or some other cluster later on down the road. So I'll briefly talk about the MLS, the current machine learning architecture as well from AWS infrastructure perspective. We again have a time-based trigger because you have to retrain your models now and then. This training is, there are two Docker containers here. One is for pre-processing. So again, read the data from the database, historical data, do pre-processing. I want to add something on the pre-processing here from machine learning perspective. We added data binning, we added anomaly detection, outlier detection, we added risk modeling as part of the training job. We added the ensemble techniques at inference. So those things were not part of the legacy system. We added new systems, new algorithms to the new machine learning system. And because of this modular architecture, we were able to add features as and when we needed, rather than creating new new pipelines. So another interesting thing is, if you know, there are parallel training jobs. So we do a pre-processing on the entire data set, and then we parallelize our training to different batch jobs. The interesting thing about this is our training execution times are pretty less. We don't have to wait for a couple of days to get all our training done. Within a couple of minutes to hours, it's done. And the reason to store these models in S3 is that we want independent separation of concerns. If you come from a software background, you'll understand separation of concerns. The idea behind it is that the module on the left and the module on the right, they are separated and they are doing their own job. The glue between them is just these models. So tomorrow I can replace this with some other infrastructure, other service, but still it will work because the models are here. And this is a loose coupling between the two systems. Okay. Another improvement which we have done is, in the legacy code, the Lambda, during the invocation of the Lambda, we had real-time download of models from the S3 bucket, which can invoke a network delay, which it can invoke some downloading time. Sometimes the models are small, sometimes they're large, so your API performance can degrade. But in this, since it's a Docker container, when the Docker boots up, during the boot up process itself, we can download all the models, and this significantly improves our response time, because we can use a cache within the Docker to get all the models in real time. So I also want to touch base upon the evolution stages which we went through. So I'm just comparing over different verticals what our system was. So the architecture of the legacy was a monolith. You change something and we break something somewhere else. You come to know later on in the cycle. Bug triaging is very difficult. So slowly and slowly it becomes, bit of a nightmare to manage it. The intermittent solution is a hybrid. One service is still a monolith, but the new ones are, microservice architectures. And then the current one is a complete microservice architecture. The infrastructure initially was, most of them was manually created. In the second stage, in the intermittent stage, we had the legacy manual, plus we started doing a lot of Terraform code. Basically, create your infrastructure as a code. So anything you can recreate your infrastructure at any environment you have. Monitoring, there was no monitoring of the legacy system. Monitoring in the sense, how is your model doing over time? How is your API performing over time? How many, let's say, 500 HTTP 500 errors are coming? Is your API down? Are your batch jobs failing? In the intermittent, we had some basic monitoring. We could monitor on the new service here and there on the API responses. We could monitor on the batch jobs. And in the current architecture, we have real-time dashboards. I'll show a picture of that later on this presentation. One big effort which we have is on these verticals. We were always testing in the legacy system before pushing to production with couple of smoke tests, manually testing it out. Okay, deployed it. Okay, hit your Lambda with these JSON parameters, and then okay, things are fine. It's okay, it's working. In intermittent system, we had a mix of manual and unit test. Now, in the current system, we have automated testing, regression testing, and we do still some manual testing, but most of them is all automated testing. The good thing about this is we are again refactoring this current system to some extent, and this is helping us, catch issues much before, and this is helping us to track our progress. Are we progressing on the right track? CI/CD is a big achievement here, because every PR we push in the code, this is triggered. The Jenkins jobs are triggered to catch any issues beforehand, and we have automated deployment. We have a need-based deployment. We don't need to deploy our code every time it's pushed to the branch. Whenever we feel the models will make sense, we push it. We deploy it. Sorry. Code coverage is another big thing for us. We had 0% code coverage in the legacy system, and over the period we have achieved 85% code coverage, which is not much heard of within the machine learning teams. Coding guidelines. So with current service, we are following very strictly PEP 8 standards. So anyone on the team, is not supposed to do anything which is his own way of writing code. You have to adhere to PEP 8 standards. And I'll also show you the PR checklist which we have. Some of the best practices which we followed, I think I had some questions on the HOA app on this. So the way we went about this project is we're not breaking everything today. We went about different stages. But when we had to do a development of pre-processing API and the training, it cannot be a sequential development. It has to be a parallel development, in the sense, if you wait for your pre-processing to be done, it takes time, and till the time you cannot do training, till the time you cannot do API, that's not going to work. That's going to take too much of time. So have strict contracts. It's like an interface. So if all the three services know their interface and they follow the interface, you can do parallel development. And this helped us a lot in delivering the product on time. We focused extensively on the CI, as I said, 85% code coverage. API performance testing, that was again a big thing. The legacy API, since the code was not very optimal and it had a lot of suboptimal features, we used to have around 8 to 10 seconds of response time. But with this current architecture, we are having roughly 500 millisecond and less. So we have made a huge improvement of 10x to 20x. API auto scaling. So if you guys are aware of Lambda, Lambda is auto scalable. It scales up to 1000 concurrent requests per time, per request. But with auto scaling policy for this, because we created our own Flask app which is running in a Docker container, we ran extensive tests to figure out what are the auto scaling limits, at which point of the time the API needs to scale. And with that, even this auto scaling policy is part of the Terraform code or the infrastructure code. Infrastructure as code, what is meaning of that? So if you guys are aware or you have worked with cloud or you have some sense of it, most of the development with cloud, you can create your infrastructure, your resources on, let's say, AWS or GCP from the console itself, or you can create from the command line itself, right? But again, the problem is someone on your team might change, or someone else on the other team might change some resource, some policy here and there, and you will be blocked, or you will not even know what happened. With infrastructure as code, think about your AWS infrastructure, GCP or Azure or whatever it is, as a code. The Terraform will create that code for you, create that infrastructure for you. So you don't have to worry about who changed the system or what happened to it. You can always rebuild it if required. And any changes to the infrastructure will be done via the code. It will not be done manually. Mandatory checks for each PR is basically, I'll come to that. And another is automated need-based deployment. Whenever we need to deploy code for retraining, we will deploy it. Okay, so as I was talking about, these are the dashboards in the new system. You can see over the different trainings, we have 2 trainings as comparison. The accuracy of our models has increased. So this gives the indication, I showed an increase, I didn't show a decrease for sure. But if it decreases, then we can catch what happened and we can go and investigate further. This is our PR template checklist. So each PR will be reviewed only if you have these parameters, which is you have the ticket URL, who is the reviewer, have some label for it, add the description. Okay, unit tests, make sure the unit tests are included. So before even the PR is raised, the person has to run all the unit test cases, they have to pass, and have documentation, updated documentation. And I'm happy to say this is just not the software guys. The data scientists on our team are also doing the same thing. If they do not have unit test cases, we do not take their PRs. So this is a good software practice which we are doing within the team. And this is the CI pipeline for us. The moment the PR is submitted, we run all the automated test cases, and if anything fails, we get to know and it passes. Code coverage. Code coverage is basically, this is just a snapshot. On the left hand side is the directory structure of our code, which I could not share, but this says over different modules of our directory what is the code coverage, and overall it is 85% plus. Okay, so before I end, I want to thank the data science team, ML team at TradeRev, both the current people, the previous people, because we work as a team and we succeed as a team. And when we talk of other teams, so across the company we have different teams working with us, the product team, the marketing, the sales, the other business teams. Without their support, it's not possible to build a product. And open source community. I think we stand tall on the shoulders of giant, and our success is a testimony that open source software really helps everyone. And with that, I'd like to thank you all for attending my talk.